Hello, ladies and gentlemen. We are going to be taking a look at some standing waves today. And in your homework today, you will also receive some, you'll also get some more practice with just using the general equation for wave speed that you looked at yesterday, which was v, or velocity, wave speed, is equal to wavelength times frequency. So you get a little more practice with that. But we'll look at some standing wave stuff today in a couple different scenarios that can happen with standing waves. So today you'll go through these slides. You'll have your day two exit ticket and also your assignment for the day as well. So just a little bit of review from yesterday. We talked about, the slides talked about superposition, or constructive or destructive interference when two waves collide with one another or they interfere with one another. And what we have here is, if you looked at this first example on the left, we have wave one, we have wave two, and then when they collide at that moment, they create wave one plus two. Now, hopefully all of you you did that activity with the graph that created a nice superimposed wave on top of each other. It wasn't as perfect and pretty as this one, but you should have seen kind of how it created that jagged type wave with crests that were a little bit higher and lower. But what we have here is when we have a crest line up with a crest, well, then you end up getting a crest that's really tall. Same with the troughs. You get a trough and a trough that line right up with each other. You get a trough that's really low. The exact opposite is true for destructive interference. So this one would be destructive interference. When you have a crest lined directly up with a trough, and a trough lined directly up with a crest, well, that's where you end up getting this flat line. Okay, they're canceling each other out. Think of it as adding the amplitudes together. Okay, so if this right here is a positive amplitude of, let's just call it +5, and this is the exact same magnitude, just in the opposite directions, in -5, you add those together, what do you get? You get 0. Okay, so just a little bit of review on that from yesterday. So moving on to, this is just kind of a cool video that you can take a look at, kind of talking about sound and breaking the sound barrier. If any of you have ever been to a air show before, I have not. I really want to go to one. But if any of you have ever been to an air show where they break the sound barrier, you hear what's called a sonic boom. And this just kind of goes into the explanation of sonic booms. It's kind of a cool video, and it's relatively short. These two videos I do want you to for sure watch, right? I definitely want you to watch these videos. This first video, the standing waves demo, is a kind of a demo that I would normally do in class. And this guy does a video where um, he makes a wave out of a string. Okay, and he makes a standing wave on a string, and you'll see what that looks like when you watch that video. And that's the exact same kind of demonstration that I would do if we were in class. And then here with the standing waves explanation, it's the second video. Then he goes into and kind of explains things that we're going to be talking about. So I'd like you to watch those first, and then you can kind of get some prior knowledge to what we're going to be talking about here. So hopefully you watch those videos, and in those videos, in the explanation, he talks about difference between nodes and antinodes. Okay, nodes are the areas where on the standing wave it's got this amplified area. That's the way I remember it. Is antinode is A, or antinode starts with an A, so that is amplified. And then the node starts with an N, so that has no energy. That's kind of how my useful little tip to remember those. So antinode is amplified, node has no energy. Okay. He talked about fundamental frequencies and harmonics. So when he had that string going with just one big, I sometimes call these all these numbers over here I call them number of, if you ever hear me refer to them as bumps, the number of bumps on a wave. So like this fundamental has one bump on a wave. All right. So every time you have one bump, that is your fundamental. Okay. Two bumps would be it has one full wave. All right. And he talked about how that fundamental is half of a wavelength because that would just be like having one crest or one trough. Okay. Versus with the second one here, let me get a better color. With the second one here, we have a full crest all the way down to a trough and then back to our equilibrium point. So that is one full wavelength. So whenever you're in your um, your second harmonic, that would be your full wavelength. Okay. So now these are for standing waves, or we'll talk about waves traveling through an open tube. It's another way that that we use these. So that's where one of our equations comes into play. So remember, your fundamental is half of a wavelength. Okay. So what we can say then is that the wavelength of the fundamental is always going to be 2 times L. And L is going to be the length of your string. Or sometimes it might be the length of the tube if we're talking about a tube, right? Because we'll talk about sending waves down a tube, and I'll show you that in a second here. That also might be, L could also be length of tube. Okay. And then your harmonic wavelength, all right, if you're trying to find a specific if you're trying to find a specific wavelength for any given harmonic, you're going to take 2 times the length of the string and then divide it by whatever harmonic number it is. All right, and I'll show you what those look like here in a second. All right, and I think he did a pretty good job of explaining that in the video too. So what you're going to end up getting is you will get one, if we're looking at our first harmonic, the wavelength is 2 times the length of the string. If you're looking at your second harmonic, then your wavelength is just going to be the length of the string because that is one wavelength, right? And then from there, we can just keep making fractions, basically changing the denominator. And that's all we're doing. So it's just going to be 2 over 3, 2 over 2, 2 over 3, and then 2 over 4. Then for this one, 2 over 4. All right, think back to basic fractions. 2 over 4 just turns into 1/2. And then you have 2 over 5. And you could keep going with this to figure out each individual wavelength. So the wavelength for the sixth harmonic would end up being 2 over 6 or 1/3 L. Okay, and you can just keep going on and doing that forever and ever and ever as long as you're still able to see those harmonics and identify those harmonics. Okay, so our generic formula for frequency, right, when we're looking at solving for the frequency when we know a couple of other things. Now, on your equation sheet, you're going to notice that this one is labeled as frequency open. All right, so this equation can be used for either an open tube or just like here, it can be used for standing waves on a string. Okay, and this equation basically comes from the fact that we know if we were to take our general equation for velocity is equal to wavelength times frequency, and we change it to solve for frequency, what we end up getting is velocity divided by wavelength. Okay, well, if we know that that wavelength is going to end up being, let me think about this. That wavelength is going to end up basically being 2 divided by n, which n is my number of bumps, all right, or basically whichever harmonic you were in, multiplied by L, or length of the string, then the equation we will end up getting is n, one second here. Sorry about that. So we will be getting n times v divided by 2 times L, or length of my string. So remember, this is going to be for either a standing wave on a string, or it could be for finding the frequency of a wave going through an open tube. All right, so let's take a look at what that would look like. So if I were to ask you, what is the fundamental wavelength of this given problem here? And that one's pretty easy, because if this whole length here is 3 meters, well, then the wavelength of my fundamental is going to be 3 meters. And then for wavelength of the third harmonic, since I know that I'm going to have, so I'm looking for that wavelength. And remember, if I don't want that. If I were to go back and take a look at my third harmonic there, remember it is 2 over 3, or 2/3 of the string length. So I would have 2 over 3 times 3 meters. So what I'm going to end up getting there is my wavelength is just 2 meters. And then finally, what we have here is wavelength is equal to, now this one is going to be 2/5 times 3. And that should end up getting you 1.2 meters. Okay? All right, moving on to, so this is just showing you that open tubes are going to have the exact same equation as that, the frequency of the standing wave on a string. It's just going to look a little bit different. Okay, so when we had a standing wave on a string for the fundamental, we had a wave that looked something like this, where we had one big antinode in the middle, 2 nodes on the ends here. All right, well, when we're talking about a wave going through an open tube, instead of having an antinode in the middle, the only difference is now we are going to have a node right in the middle there, and our 2 antinodes are going to be on the end. But nothing changes as far as the length of the wave goes, because that is still half of a wave. And then the second harmonic is still 1 full wave, and so on and so forth. Okay? So all of these equations are still going to be the exact same. All right. And then the last thing is talking about tubes closed on one end. So now when you have a tube that is closed on one end instead of being open, now that's going to change things a little bit, because now instead of having half of a wave, we're going to have 1/4 of a wave in our fundamental. So now we're going to have a node on this end, and then where the sound is going in, we would have an antinode right here. And that is only 1/4 of a wave, because if I were to complete this whole wave, let's see if I can do this, would end up looking something like this. Or, yeah, so it would end up looking something like this. There's a really good lab that we normally do in class that has to do with tubes being closed on one end, and I have you solve for the speed of sound. Really upset that we don't get to do that one. That's a fun lab. But hopefully you understand kind of how this works. The wave is just reflecting differently off of a tube closed on one end. And that's the only difference here. Okay, so the way that this changes our equation, the only difference is instead of our fundamental being half of a wavelength, and now it is 1/4 of wavelength, this will be, let me change this. This will be my frequency on a closed tube. And this is on your equation sheet as well. The only thing it changes is we still have n, which is your number of bumps or your whatever harmonic you were in, multiplied by velocity. And now we're going to divide it by 4 times my length. All right. So this is basically saying 1/4 or 1/4 because that fundamental is 1/4 of a wave. Okay. So that's the only difference there. Oh, shoot. Let's try that again. I want to go back. Sorry. So there's this is some of your wavelength equations, what they would look like for your closed tubes when you're solving for those. All right. So now you will have 4 over whichever harmonic you in. So this one would be 4/1. This one would be 4/3, 4/5, 4/7, 4/9. All right, so your assignment for the day, complete the exit ticket number 2. And then there's an assignment number 2. Just an FYI, you are not doing, there's 3 different parts to this assignment. There is, and I forgot to put this in here and I can do that. There is a section, I'll actually just go to it right here. There's a section that is about just speeds of waves. There's a harmonic section. So you're going to be doing numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so you're basically doing everything except for this intensity section. We're going to save this intensity section for tomorrow, so don't worry about that right now. A few things to note about today's assignment is that the speed of light for all light, so when we're talking about light, it's any kind of electromagnetic radiation, so whether it be visible light, radio waves, microwaves, could be UV light, any kind of light travels at 3 times 10 to the 8th meters per second. And I think both of these conversions are in there, but just so you know, 1 nm or 1 nanometer is 1 times 10 to the negative 9th meters. And then megahertz is 1 times 10 to the 6th hertz. Okay. So if you have any questions on this sheet, please make sure you let me know. You guys have been doing an awesome job of asking me questions, and hopefully I have been answering them well enough for you. So keep those questions coming. Hopefully you all have a great day, and we will see you tomorrow. Not literally. You'll hear from me tomorrow. Have a good day.